Hello friends, welcome to Mu Lessons. Today we have come up with another topic for thermodynamics, that is the laws of thermodynamics. So before reading the laws, you must be aware of what are the types, what are the processes and how the state changes in thermodynamics. So to govern them all these things, there are particular laws which are made, that is the zeroth law, first law, second law and third law respectively, for particular different purposes. So we'll go one by one in this video. So the first, we'll start with the zeroth law of thermodynamics. This law states that if object A, consider an object A, is in thermal equilibrium with object C, and object B is in thermal equilibrium, separately thermal equilibrium with object C, then A and B will be in thermal equilibrium with each other. That means you can consider these pictures like if in this case A is in thermal equilibrium with B, that is no heat flows in between them, and that is the main condition for staying in equilibrium condition. And similarly B and C are in thermal equilibrium, so we can directly say that A and C will also be in thermal equilibrium. So this is the basic fundamental about the zeroth law of thermodynamics. Now coming to the next law, that is the first law. This is a very well known law as laws of conservation of energy, or better known as the first law of thermodynamics. So what happens in this case is, if you consider this diagram, let this cylinder has internal energy U1 and some amount of Q is given to it. That means if a system's volume is constant and heat is added, then there will be a decrease, there will be increase in the internal energy. Means the volume of this systems are constant, but then also some heat is added, like in this case Q from the second diagram. So what is the resultant? The internal energy of the net increases. So further we can say it like this: the change in internal energy equals to UF minus UI equals to Q. Now before going to some of the different laws, we will explain about some of the different terms like enthalpies related to this chapter. What is enthalpy? This is rather the heat of reaction. The enthalpy of a substance is a measure of the energy that is released or absorbed by the substance when bonds are broken. So when bonds are formed, some energy is released, and when these bonds are broken, so energy must have to be absorbed, so that there is a conservation of energy. So that is what we call the enthalpy. Now del H, that is the net change in enthalpy, is given as the summation of the enthalpies of the products minus the summation of the enthalpies of the reactants. Now consider a chemical reaction system. The small box you can see, this is the system, and the rest part is the surrounding. So both the system and surrounding comprises the universe, together makes the universe. Now consider we have this system for our own, and this is the surrounding. When heat leaves the system, that means when system exerts heat, it is known as exothermic reaction. So in this case del H will be negative. Del H will be negative for the system, but it will be positive for the surrounding. That means heat exerted by the system will be negative and heat going into the surrounding will be positive. Similarly, the reverse case, when heat is absorbed by the system, that means the surrounding is giving the heat and system is absorbing the heat. So in this case, it is an endothermic reaction, and del H will be positive for the system but negative for the surrounding. So you are quite clear about the rate of change, the net change in enthalpy in system and surrounding. Now coming to again our topic, that is the first law. Now if a system does work on the external world and no heat is added, its internal energy decreases. This is one stage, rather you can say, of the first law of thermodynamics. So what happens in this case? There is an insulation and some mass is kept and the internal energy is E1. Now no heat is given to it, but it is doing some work. So in order to conserve the energy, the internal energy of the system decreases and it becomes UF, that is equals to initial energy minus the work done. Now combining these laws, the first law of thermodynamics, the change in the system's internal energy is related to the heat Q and the work, and this internal energy is given as del U equals to Q minus W. So it is vital to keep track of the signs of the Q and W. So very important to know when these signs are positive and negative. So there is a brief tip. Whenever a system gains heat, as we have seen in the previous diagram, whenever systems gain heat, Q is positive. Whenever system loses heat, Q will be negative. And when work is done by the system, it is positive. Work is done on the system, that is negative. So these are the four basic considerations, or you should keep track of the signs of this Q and W in order to learn how the systems are behaving according to change in Q and W. Now one example for this first law of thermodynamics. The internal energy of the system depends only on its temperature. The work done and the heat added, however, depends upon the details of the process. That means you can see this woman, this lady is walking. So as she is walking, there is exertion of heat, that Q becomes negative. And rather you can say in this case work is done, that is W is greater than 0. So in order to conserve the energy, the net internal energy decreases. Now we'll talk about some thermal process. We'll assume that all the processes we discuss are quasi-static. Quasi-static means they are slow enough that the system is always in equilibrium. We also assume that they are reversible processes. For a process to be reversible, it must possible return both the system and surrounding to exactly the same states where they started. So that is the basic definition about reversible process and quasi-static process. So this is an idealized reversible process. The gas is compressed. You can see the first part, the gas is compressed, the temperature is constant, kept constant. So heat leaves the gas. This Q is exerted from this gas. But as the gas expands, it draws heat from the reservoir, returning the gas and the reservoir to the initial states. From the second diagram. So these are two different processes, or you can say two different stages of this thermal process. Now what is the work done during the net change in the volume considering this thermal process? So in this case the pressure is kept constant but the volume increases. So the work done is W equals to P into V2 minus V1, that is del V, net change in volume, or you can say P into Vf minus Vi. This is the pressure volume diagram. At constant pressure, the volume is increasing from V1 to Vf. So in this case, small analysis will help you in studying about thermodynamics, and you will be quite clear about how to deal with these problems. Now in this case, what happens? The volume stays constant, nothing is moving, so no work is done. Whenever there is no change in volume, strictly remember there is no work is done, that is W is equals to 0. And in this case, you can plot a graph, that is from the initial volume, the volume remains constant, but then pressure increases. And in this case, no work is done at constant volume. Next, the thermal processes. If the temperature is constant, the pressure varies inversely with the volume. This diagram shows how the pressure will vary inversely with the volume whenever the temperature is constant. This is basically on the basis of the laws of the various gases law, Boyle's law, Charles' law. Now for that case, if you want to consider the work done, now there is a logarithmic decrease of this graph from V1 to Vf. So the work done in this case will be nRT ln Vf minus Vi, Vf by Vi. N into RT ln Vf minus Vi. N is the number of moles, R is the gas constant, T is the absolute temperature, ln of Vf final volume minus by initial volume. Now in case of an adiabatic process, that is when no heat is changing, that is del Q equals to 0, in which no heat flows in and out of the system. So the adiabatic PV curve is similar to that of the isothermal one. Isothermal case also there is net change of temperature is 0, but it is quite steeper, that is the slope is very straight. One way to ensure that the process is adiabatic is to insulate the system. You can consider this both of this diagram. There is an insulation, gas is compressed, and it is this is an example of adiabatic process. So no heat is exerted from this, even if there is a compression of the gases. As seen before, there was some heat exerting from the cylinder, but in this case, as del Q equals to 0, no heat comes out, just the pressure and temperature increases. Similarly, if it expands, then pressure will decrease and temperature will decrease in case of expansion. Now another way to ensure that a process is effectively adiabatic is to have the volume change occur very quickly. It means the volume will change very quickly. There will no time to flow in and out of the system, no time to change the heat and in and out of the system. Burning of some material and just pushing it the piston down. This is one more example. There is no time, exactly no time for the flow of heat in and out of the system, but it is compressed. So in this case what happens, the temperature increases and the pressure also increases in the second part. Now here is a summary of different types of thermal processes. Constant pressure. In case of constant pressure, W is equals to P del V, that is the volume changes. So Q will be internal energy, net change in internal energy plus PdV work. In case of constant volume, work done equals to 0, and we substitute here work done equals to 0, so Q will be is equals to net change in internal energy. For isothermal case, work done equals to Q, so that is equals to net change in internal energy will be 0. In case of adiabatic cases, no heat flow takes place, the work done is equals to minus of del U, that means Q is equals to 0. So these are basically different types of thermal processes. We'll come across it when we'll study about these numericals. Now coming to the specific heat for ideal gas, constant pressure and constant volume. So you are quite aware of this term specific heat, constant pressure term, constant volume, Cp, Cv, Mayo's formula. So specific heat for ideal gases must be quoted either as a constant pressure or constant volume. Means you have to consider either it is a constant pressure or volume. Let Ti is the temperature, Q is given the heat, then Tf changes from the T changes from Ti to Tf, and the final temperature is equals to Ti initial temperature plus net change in del T. So we can write the heat supplied QV will be equals to N into Cv, that is the specific heat at constant volume, into del T, and this Cv will be QV by N del T. Similarly at constant pressure, in this case the pressure is kept constant, so we will consider this QP will be equals to N Cp del T, that means N number of mole. Cp means specific heat at constant volume and net change in temperature as the heat is applied into it, and final state becomes Ti plus del T. But both Cv and Cv can be calculated for a monoatomic ideal gases using the first law of thermodynamics. So this is basically Cv equals to 3 by 2R. These are very simple, but you should remember these things. This is only for the monoatomic ideal gases. In class 12 standard you read about diatomic, how to calculate. There was some formula, I didn't remember now. 1 plus N into 3 by 2R, like that, or 1 minus N 3 by 2R. So Cp will be equals to, this is basically for the monoatomic ideal gas, Cp is equals to 5 by 2R, Cv equals to 3 by 2R, and the difference between Cp minus Cv is R. This is the Mayo's formula. There is a table regarding the Cp minus Cv, that is R value for various gases. Now this PV curve for adiabatic is given. In case of adiabatic conditions, we should remember PV to the power gamma is equals to constant, and this gamma is of very much importance, that is the Cp minus Cp ratio, Cp minus Cv ratio. So in case of adiabatic PV curve, there is a decrease in the adiabatic curve with respect to the volume. You can consider it as a logarithmic decrease or exponential decrease. Better to consider it as a logarithmic decrease. So in this case, PV to the power gamma is equals to constant, where gamma is Cp minus Cp by Cv, and this gamma comes up to be 5/3 for this monoatomic gas, and for diatomic gas you can refer the books. So basically in our studies we'll deal with the monoatomic types of gases only. So this was all about the first law of thermodynamics, various specific heats of the gases, various thermal processes, how they are changing. So in the next part of this video we will study about the second law, continue with the second law and the third law. Thank you.